Okay, this is joint work with people in Stuttgart and Trento. I'm the second author. And the first thing I wanted to say is that I work at the Universitat Pompeu Fabra. As of June, I'm joining the University of Trento. And in this workshop, I've met people whom I didn't know, both from my present university and my future university, that are working on related stuff. So a big thank you to the workshop organizers and to the Essence Network in general for that. What we are working on is the general field can be termed symbol rounding, that is connecting a symbol, in our case, a linguistic expression, an expression in natural language, with something in the real world. And language meaning, semantics, has two distinct aspects to it. So one is the conceptual, or also termed generic aspect, in which we have a concept like cat, which is notoriously vague, and it can refer to very many different individuals, including, for instance, something I didn't know before preparing the slides, hairless animals that are suited to people who are allergic to cat hair and nevertheless like cats. So as we see, a word like cat can encompass very many different individuals, okay? And this has been a source of a lot of controversy about language. Many people complain that language is ill-behaved. On the other hand, we have the level of reference. So once we use an expression in context, many times we're picking a very specific thing. So if I say this cat, meaning this cat, it's something that's black as opposed to all the other colors. It has a particular personality, it's in a given context, etc. Okay? So there's a bit of a tension between like this generic level and this like this capacity of language to pick very, very specific things in the world, okay? And we are interested in the interplay between these two aspects of language because both are really constitutive of language and both are necessary for like many applications, which we'll come back to in the end. So what we will do is to take a semantic representation at the conceptual level and map it to another semantic representation at the referential level. Okay, so I'll go over the two systems now. On the one hand, there's like, I mentioned that this approach in a couple of questions I asked. The conceptual representation that we will be using is so-called distributional semantics, which is a hugely successful and popular approach to meaning in computational linguistics or natural language processing and cognitive science alike. It hasn't really impacted linguistics so much, and maybe people in AI who are not working on language are not familiar either with them, but anybody else really like, this approach has been really, really, really successful. And so the idea is that the context in which linguistic expression appears gives a lot of clues about the meaning of an expression. This is the underlying hypothesis. So here we see, for instance, a bunch of sentences containing the word cat, and we see Siam cat, black cat, birds, goldfish, dogs, rabbits, in the same context as cats, etc., right? Pet in the context of cat. So we see that we get a lot of clues about the meaning of cat. So what distributional semantics does is it takes instances of a word in context, of a linguistic expression in context, and then it builds a vectorial representation from it. The underlying mechanism is very simple. I don't have time to go into it, but the idea is this. So the vector that we're going to build is going to be built up from the context. Simple approaches are just counting words in the surrounding. So one dimension would be pet, another dimension in the vector would be fish. And you just count how many times cat occurs with those, and that gives you a vectorial representation, okay? There are more complex approaches nowadays, including neural networks, but that's the basic idea. So what do we get out of this? We get a vector for cat, a vector for dog, a vector for tiger, etc., for any number of words. And these vectors are like the same kind of thing that Jana showed in her presentation, just a list of numbers. The difference is that instead of generating them randomly, we are regenerating them from data naturally produced by humans, okay? And that gives us a lot of power. First, we induce the semantic representation. There's no need for any human to manually intervene. And second, it's a representation that makes a lot of sense, okay? And once you have those vectors, you have a representation in a multidimensional space. So here is a simple 2D dimensions because we can really represent 300 dimensions visually, easily. But the idea is that in the space that results from these vectors, cat will be nearer to tiger than, say, to, I don't know, car, which would be there, or even jaguar, okay? And cat is very near in this hyperspace to dog and other animals. Is that more or less clear? Well, I don't have really time to go more into it, so I'm sorry if that's too, but that's the idea. Okay. So this will be, and again, this is at a conceptual level, because it can tell you generically that cats and dogs are similar because they occur in similar contexts. Cats and tigers are also similar because they occur in similar contexts, okay? But it cannot tell you anything about the specific cat that you saw that is black. It will tell you that maybe cats are black or white or brown, but it cannot tell you anything. And by the way, these kind of representations, they can also be extracted from other types of things, not only text, but also like images, for instance. So it's really, really powerful. As long as you have a context, you can extract it. Okay, now, what's the referential representation? Well, just a simple database, a structured entity knowledge base. We are using Freebase, for those who are familiar with it. And the idea is that entities in a database, they are like specific entities in the world with very specific referential properties. For instance, for the country Spain, in Freebase, we have that its capital is Madrid, that one of the official languages is Spanish, that it's contained in Europe, we have a GDP, which is a numeric value, etc. These are not generic conceptual properties. These are very, very specific referential properties. Yeah? Okay. So what are we going to do? We want to go from the conceptual level to the referential level. So what we're going to do is we're going to build a distributional vector for Spain, which is like our conceptual representation for Spain, using the same mechanism as I showed for dogs and cats. And we're going to map it to a vector, a Freebase vector, so to speak. Okay? So it's just learning a mapping. Given the distributional vector, can we predict the GDP of a country, for instance? Okay? And we do it with a multivariate logistic regression model. I won't say anything more about it. If you want to, we can talk. We're also experimenting with neural network methods. Okay. For the moment, we have done countries. We're also experimenting with cities, and this is just very preliminary results, okay? The results that we got are summarized here. The only thing you need to know to make sense of the table is that accuracy goes from 0 to 1, and 1 is best. This measure here, normalized rank scores, goes also from 0 to 1, but 0 is best, okay? And here we have that an informed baseline achieves 0.79, so it's quite high. It's quite high. Our model achieves 0.86, so we are well above the baseline. And here the baseline is 0.34, and we're like 10 points lower, which is lower is better, okay? So we are actually doing this inferential step from concept to reference, okay? And we've done a bit of analysis of the kind of things that we can learn. And things that we can learn are things related, for instance, to the development of countries. Like we can predict the fertility rate very well, the internet usage, the GDP per capita. So, and these are things that you can easily imagine, no? If you have a rich country and you refer to it as rich, then you can like map this kind of like language usage to like actual GDPs, okay, values. So, to summarize, so we are mapping from a conceptual or generic representation, which we just as a methodology, we use distributional semantics, to a referential or specific representation in terms of a structured knowledge base. That's what we are doing. It's just the first step. But note, it's quite striking that conceptual knowledge in distributional semantics is really acquired from language used in context. So it's just how people talk, okay? And it could be just tags for images, for instance. And so we have shown initially that we can approximate really hard facts about countries from conceptual vectors encoded in distributional semantics, okay? The future, well, we want to have machines that can identify entities from their conceptual representations, okay? This robot mistakes a dog for a cat. We want robots that can identify lots of very different entities in the world from conceptual representations. And not only for like really domain-specific things where you can like really define the features manually, but really at a large scale. Like in distributional semantics, we work with vocabularies of hundreds of thousands of words. And we build a representation that is usable by machines, okay? So that's one of the things that you can have really large-scale vocabularies that you can play with. And that's a real, I mean, that's a must, because there's the so-called lexical bottleneck in AI, where if you want to go outside domain-specific or toy worlds, you really have to account for a hell of a lot of words, okay? The other thing we want to have is entities not only that can identify an entity given the conceptual representation, like to know what label to apply to an object, but we also want them to update the conceptual representation based on referential properties. That's something we haven't explored, but we want to do it. So note that here we had a double-pointed arrow, right? We want an interplay between the two levels. For the moment, we've gone from concept to referent. But imagine, as a silly example, I should come with a better example, but imagine that that for some reason there's a mutation and all cats start to be white. And then whenever we see, we use the label cat for a white cat. And then the next cat is also white. And then the next cat is also white, and so on. Well, at some point, our conceptual representation for a cat will be restricted to white cats, and it will exclude the others. So if we encounter a black cat, we won't apply the label cat to it. And that's an example of how referential information about the actual reference in the world really influences the meaning of the concept or the meaning of the word. And this is a silly example, but that's something that happens in language. So concepts evolve based on what people apply them to. And that's it. Thank you for your attention. Hofstadter, oh, yeah. Mm-hmm. 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 Like a concept. You know, you caught exactly the weak point. I was hoping for it to be. No, really. No. I don't know if it's a weak point, but it's certainly something that it's a missing step in what I presented. Okay, I was hoping that, it's not true. I mean, it's something I realized actually when writing the paper. And it's true, because like the examples I put for distributional vectors are of like common nouns, like dog and cat. And then suddenly I build a vector for a proper noun, Spain, which is a specific entity, and I call it a concept, okay? So I think this taps onto something that I still cannot wrap my head around. But so when I talked about it with my co-authors, they said, well, okay, so the distributional representation for Spain is still a conceptual representation in the sense that, for instance, it can yield like intuitive similarities between countries. That's something that we have tested. Our distributional model achieves a correlation with the distance, the geographical distance of between countries, the log of the distance of 0.64, minus 0.64. So, okay, countries that are more similar in distributional space are also more similar geographically. Sorry, closer geographically. The exceptions are things, it's amazing. It's like we get the border between Europe and the north of Africa. Okay, these are countries that are very far away in the distributional space, but very close geographically. So it makes a lot of sense, right? And so what my authors say is, okay, one thing is what you, like your concept of Spain is, which you have built up across many interactions. And then the other is some hard facts that people can tell you. Like I can tell you Spain was founded in not sure, I was going to say 1984 for some reason. Whatever, okay? And that's a fact that you just learn, okay? Or I don't know, what other, the national anthem is whatever. So it's a hard fact, okay? But I must say that that's something that I still don't have a clear, like, answer to. But there's this intuition that even instances like this cat, they also are subject to this kind of similarity thing. You can still say this cat is more similar to this one. So it's also fuzzy in a way. It's not only concepts that are vague. It's also like, so, but again, this is something I just, realized not long ago, and I agree that it's an issue. And I would love to, I have read one paper by Hofstadter, but I will write to you for the reference of this one. Okay, we can. Thank you.